Hi, welcome to the Planetary Spectrum Generator video tutorials. I'm Avi Mandel, member of the PSG team, and I'm here to guide you through the instrument and noise module for PSG. As a reminder, PSG allows you to compute spectra at a broad range of wavelengths from the UV and X-ray all the way up to the submillimeter. And it includes realistic instrument and noise simulators for a wide range of different types of instrumentation, which I'll be discussing in this video. For more information, you can refer to Chapter 8 of the PSG Handbook, available on the PSG website and in hard copy. The total noise in a simulation can be generally defined as a linear combination of three main noise sources: the scene or target fluxes, including the planet and the star, background fluxes, such as Zodi or telluric contributions, and then detector or systematic instrument noise sources. The driving parameter for the first two components of noise, the planetary, stellar, and background sources, is the total photon rate falling on the detector, which combines the photon flux from the source and the background, the instrument throughput, the collecting area of the telescope, the spectral width of a simulation pixel, and finally, the field of view of the total aperture. So, the final noise component is the detector and systematic instrument noise. Since each detector technology introduces noise in a particular way, PSG includes several different detector and instrument models to capture this instrument diversity. Each detector noise model depends differently on the observed flux rate and the detector and readout characteristics. So it's important to define an optimum integration strategy, including factors like the number of exposures, the integration time per exposure, for your specific detector noise model. Let's start by discussing the determination of the flux contribution from the host star and planet, since this is actually dependent on the geometry module that's described in Chapter 2 in another of these tutorial videos. If the distance to your object is defined as less than 0.1 parsecs, then the only object considered to be the providing flux in the PSG field of view is the planet itself. In this scenario, the parameter geometry planet fraction defines the fraction of the planet's observable disk that is within the field of view, since this defines the fraction of the planet flux capture. However, if the distance to your target is more than 0.1 parsecs, the parameter geometry star distance defines whether the host star is within the field of view or outside of it. Finally, the parameter geometry star fraction defines whether the star is being occulted by the planet, as in geometry, such as the primary transit of a transiting exoplanet. Then, moving to the instrument module, you can then select the telescope instrument template from the menu next to the top title of the module. There are templates for many different existing and conceptual observatories currently included in PSG. Instead, if you're inputting your own new instrument settings, you can just define the wavelength and the resolving power values directly. The resolution can be implemented either as a boxcar methodology, where all the flux from a single resolving element is binned into a single pixel, or with a Gaussian kernel convolved with a much higher resolution spectrum to produce an accurate line shape. We highly recommend choosing the boxcar to start out, since it is much faster and produces a optical or an actual instrument resolution for your final spectrum, rather than the much higher sampling that you get with a Gaussian kernel. You can then select from a wide variety of generally used astronomical units for your calculated fluxes, radiances, and output intensities. Then you select the type of observatory format, such as a standard single primary aperture, like a telescope or a collecting dish, or something more complex, such as an interferometer setup or a coronagraph observation. There are several parameters that define the overall aperture size, including the background zodiacal light and the total collecting area. Finally, there's a section on the calculation of the instrument contributed noise, including the detector noise and the thermal background from the instrument, as well as the telescope surfaces. All the fields in the instrument module are filled with default values for each setting, so it's easy to get started even if you've never used PSG before. On the other hand, PSG allows you to insert tables of values for important parameters such as your total throughput as a function of wavelength, your coronagraph contrast, etc. So you can also create very detailed instrument calculations yourself. We encourage you to explore the handbook in detail and also to check our other learning videos and online material to help educate yourself in the full potential of the PSG simulator. Thanks for watching and good luck.